last talk leads naturally to the next talk of Professor Hagai Netzer. Hagai Netzer got his BSc in physics here in Tel Aviv University, and 3 years later, PhD in astronomy at Sussex University. He is a member of Tel Aviv University, and his work includes quasars, active galactic nuclei, star-forming galaxies, some of the pictures we saw here, and massive black holes. He has written also more than 200 scientific papers, and he won several prizes and awards. Hagai, please.
So I'm going to talk about black holes, supermassive black holes, the largest we know, over 13.7 billion years of evolution. This is the time we think elapsed since the Big Bang. This is the most extreme, perhaps the strangest object in the universe. It's the extreme case of gravity, when space-time curves so much that even light cannot escape the region. Some of the known properties of black hole is that when you look at it from the outside, you really don't know what's inside. It can be a man, it can be grapes or bicycles. From the outside, you can only measure the mass of the black hole and 2 other properties, its spin and charge. And I'm going to tell you a little bit about black hole research at Tel Aviv University, but because it's going to be a history type of lecture, let me tell you something that NASA announced about the history of the universe just a week ago. They announced, as they claim, that the galaxy, the furthest away object in the universe, has been found. You can follow the object from the left to the right to the bottom right, and the claim is that this object started, it's a very young galaxy, it started just 500 million years. That's a very short time in terms of the life of the universe, 500 million years after the Big Bang. It's this very unimpressive, tiny little patch that you see there tells us everything or a lot about what happened just 500 million years after the universe started. So I'm going to tell you a little bit more history, but using this time black holes more and less galaxies. But the way I want to introduce the properties of black holes, and there are several ways of doing it, is to talk to you or to mention to you what we know about various ways of producing energy. And I want to measure the various ways, the efficiency of the various methods, by using Einstein equation, trying to use the equivalence of energy and mass right here at the top. And for example, conventional fuel, the one we use in our cars and in our other appliances, only use 1/1000th of the energy. If you convert mass to energy, you only use 1/1000th of it. If the energy that you get is only 1/1000th of it. If you go to nuclear reactions like nuclear fission, it's 0.1 of 1%. That's an awful lot compared to 1/1000th. And if you go to nuclear fusion, which we cannot do except for hydrogen bomb, it's 1%. So 1% efficiency is an extremely high efficiency. I wish we had that in fusion. We don't quite do it. But let me show you what nature can do. And I want to do it in such a way. Suppose this is a black hole, an area in space, a place in space where gravity is extremely, extremely large, and we want to get close to it. So I'm going to take a piece of mass, this 1m, and try to drop it into the black hole. And now let's do a very simple exercise. And if you have difficulties doing it, just ask these kids around here. They will help you because they're already in Kita Tet, so they know how to do it. So what I do is it's a very, very simple exercise. What we have to do, we have to use what we know about gravitational potential energy. This is the equation. You don't need to know the equation. All you need to know is that this little r there is the distance from the object that you want to look at. For example, our distance from the sun. And then you ask the question, if you take this value of r and plug it there, how much energy will you get out? So these kids have already done the exercise, I'm sure, and the answer is E equals exactly mc squared, 100%. The only problem with this answer is that it is absolutely wrong. You cannot get anything from that, because if you take this piece of material and drop it onto the black hole, you get nothing. It'll take all the energy with it, and nothing will come out. So don't try to use this as an engine, because it will give you nothing. But nature found ways to produce energy by this process, except for a tiny little addition, that can produce as much of 6% and sometimes even 40 and 42% of the energy. If we could use that, that will be the most efficient energy production mechanism in the universe. And let me show you how nature does it without going into the detail. The idea is that you drop something onto this black hole, a very, very compact object with very strong gravitational energy, but on the way you force the material to collide with other pieces of matter, and these collisions will heat up the matter and produce a lot of radiation. So nature knows how to produce up to 40% of the rest mass energy of particles into energy, into radiation, if you drop it to a black hole via these processes. So black hole research has become a very important part of astronomy for two reasons. One is the one that I told you about, is because we learn physics that we could not possibly learn any other way. The other thing which is important, and in fact I'm going to focus my talk today about, is the history of the universe looking through the eye of the black hole. It happens that we now know that black holes, especially the very massive black hole, play a very important part in the history of the universe. So I'm going to take the second aspect and tell you about it in 20 or so minutes, because I cannot tell you about everything in such a short lecture. So I'm going to start with the very first stars and the very first black hole, objects that were born immediately after the Big Bang. Again, the Big Bang was about 13.7 billion years ago, and the first stars were born about 3 or 4 or 500 million years after that. And we know they are very extremely large stars, and we know that they exploded in what astronomers call supernovae after that, and we think that some of them, perhaps most of them, left behind a remnant, which is part of the mass of the star, which was a black hole, a very, very compact object that retained about 10% of the mass of the star. So if the first stars had a mass of about between 100 and 10,000 times the mass of the sun, astronomers measure mass in units of the mass of the sun, then the black hole mass was perhaps, we don't know exactly, something like between 10 and 1,000 solar masses. Today, when we look at the sky, we see many galaxies, and in the nearby galaxies, we now measure, we now see, indirectly see, we see the influence of much more massive black holes. We see influence of black hole that can be 1 billion times larger than the sun. So we must understand, or what we're trying to do is find the details of the process that started from a black hole which is perhaps 1,000 times the mass of the stars and went all the way to 1 billion times the mass of the stars, over about 13 billion years of evolution. So this is the research I'm telling you about. In fact, black holes in centers of galaxies are so common that we see them everywhere. For example, the center of our own galaxy, the Milky Way galaxy, contains a black hole. It's right about where these two arrows are pointing, and here is the blow-up of the same region. We know that in the center of our galaxy there is a black hole with a mass of about 4 million times the mass of the sun. This black hole is not doing very much. We call them dormant black holes. They just sleep there. They don't do very much in terms of affecting the surrounding. Occasionally we see a blimp there from the surrounding of the black hole, but usually these black holes are not active. By the astronomical jargon, separate between active black holes and dormant black hole, or non-active. This is a non-active black hole right in the center of our own galaxy. But galaxies evolve over time. We know now, we have the detail of a very long story that follow galaxies, trace galaxies from the Big Bang or immediately after, all the way until today, and we roughly understand how galaxies evolve, how they started from being very small and going all the way to become the very large object that we see that contain perhaps 100 billion stars. Our galaxy contains about 100 billion stars. When we look at the universe, of course, we see billions of galaxies, many billions of galaxies. Here are examples of 9 of them, in fact, many more than 9, because when we look around, we see that many of the galaxies are colliding with each other. We call them merging galaxies. And the collision of the galaxy is a very important part of growth of galaxies. We think that this is the way by which small galaxies coalesce, collide, and became larger and larger in time. And this is the reason why when we look around, we see large galaxies. If we lived in the very early universe, we would have seen much smaller galaxies. In fact, nowadays, astronomers have developed tools, some people call them toys, if you want, that trace galaxy evolution or galaxy collision, if this video clip will ever start. Really? Try again. No? So what I'm trying to show you here, and Vital will fix it in a minute, is a movie which is, of course, it's not really a real collision. We don't see it, as you'll see in a minute. Maybe we'll skip it. No, that's it. Okay, so I'm sorry about that. But you see snapshots of this, as what was supposed to be a video clip, a very nice one, of various stages of galactic collision. These are not real photographs, of course. This is coming out of numerical simulations. And when we follow an event where galaxies collide and merge, this can take 1 billion, sometimes even 2 billion years. But we can look at the universe and try to identify real galaxies, the one that we see with some of the snapshots that you see in front of you. And in fact, in many cases, we see great, great similarities of the two. So it tells us that these ideas, these things are happening. And in a very general scenario that we have nowadays is that galaxies occasionally collide, they get very close to each other, they merge, and when the galaxies and all their stars merge and become a larger galaxy, 2 galaxies make one galaxy which is larger, the black holes in the center merge also and eventually become one black hole. So if we start from a small black hole, we reach a larger. So there is an evolution where galaxies become larger because they merge, and black holes become larger because they merge also. And in fact, we know nowadays that there is a very strong correlation between the properties of galaxies, or the galaxy's mass that is plotted there on the bottom, with the black hole mass in the center, and the two are correlated. You go to a larger galaxy, you see a larger black hole. You go to a smaller galaxy, you see a smaller black hole. And the remaining of my talk is going to tell you a little bit about research that is done at Tel Aviv University, which is going to study the properties of the largest black hole we see in the universe. So they are going to be right there, right at the top. They are going to weigh more than 1 billion times the mass of the sun, in fact, more like 10 billion times the mass of the sun. And in order to study them, you have to go and look at what we call active galaxies. Active galaxies are galaxies that have black holes in the center that don't sleep. They are not dormant. They accrete matter. They collect matter from the surrounding, and because of that, they are very, very energetic phenomena in the galaxy. This one on the left is a real galaxy, but you see it doesn't look anything like a galaxy because there is an extra mechanism in the center producing energy. This one here is the center of a galaxy, and you see that right in the center there is an activity going on. Black hole is sweeping, collecting matter, accreting matter, and this matter, as it goes into the black hole, produces an awful lot of energy. And this energy is exactly what we see in the center as a burst of radiation. If we follow the light of these objects, we see that the light goes up and down in time, telling us that something is going there which is very, very unstable. So these are all real observations, and all these observations suggest to us that an active galaxy, this is a galaxy that includes an active black hole, may look something like so. This, of course, is an animation. So right there in the center, there is a black hole that accretes matter very rapidly, producing an awful lot of energy, and the process may look like so. Nature has invented these processes. These are exactly the processes that can convert up to 40% of the rest mass of the matter of the gas into energy. The energy we see from the outside is radiation coming out. When we look at these objects, they provide us with a way of measuring several of the important properties of the black hole, even at very, very early time. You know, astronomers are really historians. That's very important to know. Astronomers are looking back in time. When I look at the universe, if I look at an object which is a million light years away, I see what was there a million years ago. When I look at the object which is a billion light years away, I see what happened there a billion years ago. So I'm going to tell you now that I can see so many billions years into the past, so I can actually see it. I point a telescope and I see what happened, 9 or 10 billion years ago. Of course, I cannot see what's happening here, right in front of me, because I can only look at the past. But regarding the past, we are very, very good historians. So this is, these are the result of this project in Tel Aviv that I'm going to mention in the remaining few minutes, and what was happened under the title that we gave it, The Cosmic Evolution of Black Holes, the history of black holes since the Big Bang. So the project, it's a very long project. I'm going to focus on the very last part of it. It started like in 1989, and we developed a general method to look from far away and measure the mass of very far away black holes. There is a way to do it. I'm not going to tell you all the details here because of the lack of time. And then later on, about between 7 and 4 years ago, we actually managed to measure the mass of the most massive black holes in the universe, very far away from us. These masses are, the most massive one, are about 10 billion times the mass of the sun. Enormous black hole, very enormous. They are tiny little in terms of space, but they contain a very large amount of mass, like 10 billion times the mass of the sun. And then just lately, it's a paper, in fact, that is going to be published next month. We actually looked at the object, the most active massive black hole, just 1.2 billion years after the Big Bang. Again, the Big Bang happened about 13.7 billion years ago. This is 1.2 billions after that. So let me show you some of the, before that, of course, the main, it's a group of people in Tel Aviv University over many years. I listed some of the names. The first two are already faculty member in Tel Aviv University, and the third one is a faculty member in the University of Texas. And the person who did more than anybody for this last point that I'm going to mention in a minute is Benny Trachtenbrot. He's a PhD student in Tel Aviv. I think he's sitting somewhere in the audience. I don't see him from here. So let me show you, as a final slide, what I want to, the main result of this. So here is the Big Bang, 13.7 billion years ago. Here is the Big Bang, and we are looking at the history of the universe. So the next slide is going to be very similar. The one after next, we are going to start from the Big Bang and going all the way to the present. So the present is right here, 13.7 billion years after that. So before I show you the main result and the final result of the project, some observing tools that we use. So you can see on the left-hand side a very large telescope array in Chile. We use part of that for the research. And in the middle, the Gemini telescope. These are 8-meter class telescopes. Gemini is in Hawaii, and you see Herschel on the right-hand side. We also have a space base, a part of this project. And right here at the top left, you can see Herschel original telescope, which was slightly smaller, I guess, and with a slightly less performance. And what we do, without going into the detail, we obtain spectroscopy of the material near the black hole and use it to obtain the black hole mass. So we get things that look like so, and again, you'll have to excuse me for not going into all the details to explain how we do it. This is the method that I told you was developed in Tel Aviv University, and we know how to do it. So we know how to look 10 billion to a distance of 10 billion light years and measure black hole masses. So this is the final slide, and I want to take 2 minutes to explain what you see here. So you see the same slide with some additional points. And this is a combination of several samples, several big studies that were done. All the small black points are black hole mass measurement. You can see the black hole mass here on the left. So on the left side, you can read the black hole mass. The top one are the most massive one, and again at the bottom you can see time. So time goes from the left side, which is the Big Bang, to today, which is the right-hand side. And all these points were measured. The black hole mass was measured in using the method that was developed in Tel Aviv University. And then what we did after that, this is the project 2000-2007. You see we go even further in time. We're getting closer to the Big Bang. And as we go to that, we measure, and these are already our own observations, we measure black hole masses that are even larger. You see that the mass is getting larger and larger. And this final part of the project, the one that is going to be published next month, is actually going even closer to the Big Bang. And what we find very surprising and very interesting is to see the development. You see that after the universe started, the black hole mass, if you look at the most massive black hole, gets larger and larger and larger until a certain time, this time is about 3 billion years after the Big Bang, when it starts to go down. Now all these black holes are still there, but they stop accreting matter. Material is not falling onto them anymore, and therefore we don't see them. They are there, we don't see them. So this is in fact a short history of the development of massive black hole from the Big Bang or immediately after the Big Bang until today. So that's the entire history of black hole in one slide. So let me finish here, and because it's a science and space meeting, and we mentioned, and other people mentioned, basic and applied research, I want to add my own contribution. I'm doing basic science. This is science in order to do science, in order to understand the universe. But I want to remind you, and we all know that in 1915, Albert Einstein invented or wrote general relativity. General relativity was one of the strangest theories there is. Black holes are the result of general relativity. That was 1950. And nobody, including Einstein, thought that general relativity will lead to any application, any use in everyday life. It was as far as you can imagine from reality. And nowadays, there are several applications. I only mention one, the GPS. You want to know where you are, you want precise time, you have to use general relativity, because otherwise you will be wrong. You think that you're here and you will be there if you don't correct for the result, for the theory of general relativity. So very basic science, pure science, theoretical science, can become a reality. So GPS is the result, or part of the GPS properties and accuracy are the result of general theory of relativity. 1915. Now we're looking at black holes. That's another result of general theory of relativity. I don't know where it's going to lead. All I could tell you today is about what it tells us about the history of the universe. I'm not sure if it's going to lead anything applied. But one thing I know, and it's perhaps very important, because we are sitting here in Tel Aviv universities. Universities are there to produce science, and science is knowledge. We are collecting knowledge. We are increasing the amount of knowledge. One day, in 10 years, or perhaps 100 years, this knowledge will help us all. Thank you very much.